Bismillahirrahmanirrahim. Assalamu alaikum viewers. Welcome to my channel, and today we are going to discuss orthogonal trajectories with respect to the polar coordinates, right? Because last time, in the last video, we tried to understand the same topic with respect to the Cartesian or rectangular coordinates quite exhaustively, including an example. And now we are going to move, or we'll try to have a deep insight of orthogonal trajectories with respect to polar coordinates. What exactly a polar coordinates are, we know that quite well while studying the first level of the calculus, that polar coordinates in two dimensions contains radial vector and the direction of the radial vector with respect to the positive x-axis. Okay, so here in this video we'll try to understand the derivation of perpendicular or normal trajectories or orthogonal trajectories with respect to polar coordinates. We're not going to discuss the examples, it will be included in the next video. Okay, and those who are interested in seeing the Cartesian coordinate explanation, they can see the subjective link in the description box below. Right after that, it'll be much prudent if you move to this topic. Okay, so now over here, I just try to maintain a two-dimensional plane, and I'm just trying to focus myself on the first quadrant just to make myself comfortable, and that's it. So over here I just try to draw a nice curve representing a certain function f of x, y. Okay, and I just pick up point P over here and point Q right over here, or maybe here. Okay, so I just call this point as my point P, and it is having certain coordinates x and y. Okay, like you can see that if you just move over here, it is having point x, and over here it is having point y. It's like that. So similarly, I just pick up this point and I name it point Q. Okay, and its x coordinate is represented as x plus del x. It's a partial derivative, means the difference between this point x and this coordinate x and this coordinate x is just del x, means there's a very small difference between the x coordinates of both these points. Same story is going with the y coordinate as well. This thing reveals that the distance between P and Q is very, very small. Though I have just drawn it and you can see a very visible difference between P and Q here. It's just for the sake of understanding, because if I just try to draw Q over here, it seems to be overlapped, it's hard to understand. Okay, so it's just for that sake. Alright, so this is it. Now I just try to draw here a tangent line passing through this point of tangency P. Okay, and this tangent line, once when I'm going to draw, it is going to touch the x-axis and making some angle. I call that angle C. Okay, though it spells this, but we pronounce it C. Okay, it's a Greek letter and we represent it with this notation. Okay, this is it. So let me just draw a tangent line here. Okay, here that's how it looks like. Okay, and it is making an anti-clockwise positive angle along with the x-axis, and I call it phi. Oh, sorry, C. Okay, in the same way, I'm going to draw a tangent line with respect to this point of tangency, and it is also going to make some angle with respect to the x-axis, and the difference between this angle and this angle will also be very negligible. So I'm going to represent the angle between this upcoming tangent line and the x-axis as C plus del C. Okay, so let me draw that thing also. Okay, here you go. This is the tangent line, and it's making this angle with the x-axis anti-clockwise. So the difference between these two angles of these two tangent lines with respect to the x-axis is quite less. Why? Because the difference between the x coordinates of both these points and the y coordinates of both these points are also very less. That's the reason. Okay, now what we are going to do, we are going to discuss here the instantaneous rate of change. Before moving to that thing, first of all, we'll try to join the point P and Q, and we are going to have definitely a chord, and we call that chord a secant line. Okay, so better use a different color. And this concept I have briefly discussed in my geometrical interpretation of the derivative. You can see in my calculus playlist, you can find that video too. So I will also put the link in the description box as well for your A's. Okay, so let me just join these two points P and Q. Here you go. Okay, so now what is happening exactly? But this is the secant line. Once when P and Q are at a visible distance from each other, then you can easily observe the secant line, and it is convenient and it's possible for you to find out the slope of this line by a conventional method of rise over run concept. So it's going to be y plus del y minus this. That is basically y2 minus y1 and so forth. And this is x2 minus x1. Just like that. So this things are cancelled and you're having del y upon del x. Now what happens once if your point Q move towards point P, and it gets closer and closer to point P, but it's not overlapping point P, neither it is surpassing point P. It is getting closer and closer. So there will be a distance between Q and P, but that distance cannot be observed. Okay, it does exist, but it cannot be that much visible normally. So for that purpose, we just assume in that sense that P and Q are basically one point, or they are so close they look to be a single point. So once when Q approaches to P, then this secant line will turn into a tangent line. Okay, so if I just say that this Q is approaching towards P and it gets closer and closer to P, now you can see that Q is getting too much close to your P, so it looks a single point. And this single point, if I just try to draw a tangent line over there, it looks something like this. And this tangent line is making angle C along with the x-axis. Okay, so we can interpret it in calculus linguistic in this way, that once when Q approaches to P, then the difference between the x coordinates of these 2 points will become closer and closer to 0. So it means the difference del x will approach to 0. Okay, so once when I try to apply a limit over here, if I try to apply a limit over here, then I'm going to interpret this condition in terms of differential operators like this. Okay, so this slope, this slope is interpreted as tangent of your C. All right, so this thing tells me that my tangent C is equals to, dy by dx. Keep this thing in mind. This thing tells me that the slope of the tangent line, which is making an angle C with the positive x-axis, is equals to dy by dx. Okay, we are going to keep this thing safe because it is going to be applied in further derivation. Now what we do, we are now coming to our, we are now coming back to our actual topic. Okay, this thing was actually correlated with the derivation. That's why I suggested or I thought that I should discuss this thing first, and now I'm coming to my original thing. So for that purpose, I have just managed another two-dimensional coordinate system, and I'm going to draw here another curve. Okay, this is another curve representing a function f of x. I just pick up one point over here, and I am going to represent this point in terms of polar coordinates instead of Cartesian. So instead of writing xy in ordered pair, I'm going to use r theta. Okay, so I just call this point as r theta. All right, what is your r? R is the position vector of this point joining the origin, and theta is the direction of this position vector with respect to the x-axis, okay? Or the angle that radial segment or that position radius vector is going to make with the positive x-axis. So let me just draw that position vector over here that is also called the radial vector. Here you go. So I have just extended this radial vector a bit ahead because it's going to be helpful in further explanation. So over here, it basically it is stopped over here, okay, at this point. I call this radial vector, I represent this radial vector by my r vector. Okay, so now it is making an angle theta with the x-axis and it is moving anti-clockwise, so definitely it is positive. Now what I'm going to do, I'm going to draw, now this is my point of tangency, okay, and I'm now going to draw a tangent line joining this, touching this point of tangency for this curve. So this is my nice tangent line. I just represented my t for my convenience. Okay, so this tangent line, as I told you over here, that the tangent line of the curve make angle C with the positive x-axis, or with the x-axis. I'm so used to using positive x-axis, so don't get confounded. Okay, so I just call this angle the tangent, so formed between the tangent line and the x-axis as my C. Okay, and the angle between the radial vector, okay, or the radial segment and the tangent line, I just call it with phi. I just represent that angle with a Greek letter phi, okay, just like this. Okay, so now the next step is this. I'm going to draw an imaginary x-axis over here. Okay, let me use some different color just for eye-catching observation. Okay, so I just tried to draw an imaginary x-axis passing from this point r theta. Okay, and this radial segment is moving, and according to the corresponding angle concept, whatever the angle over here will be the angle over here. So this angle is also theta. And if you just move over here, a tangent line is making angle C with the x-axis. So with this x-axis also it is making an angle C. So this thing shows that C is equal to theta plus phi. Okay, so this way we just establish the relationship between these three types of angles. All right, this is it. Now what we are going to do, we are going to focus on our phi angle. So I can also rewrite phi, the same equation keeping phi as a subject. I can write like this. Okay, this is it. Now if I just apply tangent function at both sides, what is going to happen? Tangent phi is equal to tangent of your C minus theta. Alright, now we just apply a regular formula of the tangent. Tangent C minus tangent theta upon 1 plus tangent C tangent theta. Now we know that tangent C is equals to dy by dx. That's what we are going to substitute over here and here. What about tangent theta? What exactly it is? Now for this purpose, let me just allow me to draw one more coordinate system. Here you go. So you see this is your radial segment or radial position vector. If I just try to follow, it's the projection of this point on the x-axis and the projection of this point on the y-axis, and it's touching the y-coordinate over here and x-coordinate over here. So this thing tells me this is equals to y, obviously. So if you just focus on this right triangle, then we know that tangent theta is equals to opposite side upon the adjacent side. So it is y by x. Okay, so tangent theta is equals to y by x over here. Now we are going to consult the relationship between the Cartesian and the polar coordinates. We know that x is equals to r cos theta and y is equals to r sine theta. Why this is so? Because we know that this is your r, this is your x, this is your y. So if you talk about your cosine theta, so cosine theta is what? It is adjacent side upon your hypotenuse. So that's why x is equals to r cos theta. And sine theta is equals to opposite side upon hypotenuse. That's how y is equals to r sine theta. And that's what we have written over here. Okay, now what we are going to do, we are going to differentiate both these equations with respect to theta. So once when we differentiate, here we are going to use the formula of the product of the functions. Okay, the formula of u into v, that's what we conventionally use. So it is going to be v derivative u plus u derivative of v, like this. So it is going to give me what? It is going to give me cos theta dr d theta minus r sine theta. Okay, and dy by d theta is equal to sine theta dr upon d theta plus r times derivative of your sine theta. So this thing is going to provide you sine theta dr by d theta plus r cos theta. This is your dy by d theta. Let's close it in a nice box just for a good highlight, and that's it. Okay, so you can also see now we have just managed all the possible tools which are going to be used over here in substitution. Now you can see here that at the place of your tan c you are going to write this, but this is not sufficient enough. So we are going to use implicit or parametric differentiation. So at the place of dy by dx we can replace dy by dx by dy upon d theta upon dx upon d theta. These things will get cancelled and you are having a restored form. Okay, so we are going to use this thing at this position. All right, so now let us now substitute the subjective values over here. Okay, so now tangent phi is equal to dy upon d theta upon dx upon d theta. This is your tangent psi, minus tan theta is y upon x upon 1 plus dy by d theta upon dx upon d theta times tan theta, which is this. Okay, now we are going to take a nice LCM. So once when we take a nice LCM, what we are going to have, we are going to have it. So this and this gets cancelled and you are having finally tangent phi is equals to okay, this is it. Now we are going to substitute all these values which are so obtained from here and here. You're going to put all these values over here, and then we'll solve it. We'll get the value of tangent phi. Okay, so let's substitute. Okay, we have gently substituted all these subjective values over here. We will do simply normal mathematics, multiplication and cancellation stuff. So let's see what we get right after that. Okay, this is it. So you can see that once after multiplication, we just got this stuff, and we are going to cancel this with this, and this thing is getting cancelled with this. So what is so left here is r square is coming common from these two terms. So we just take it out, and inside is left cos square theta plus sin square theta. Okay, which is definitely 1. And over here we are getting r dr by d theta common, and inside is left cos square theta plus sin square theta. Okay, this stuff get cancelled, 1r and 1r get cancelled, and we are having dr upon r upon dr by d theta. This is your, what you say, tangent phi. Alright, so also you can write your tangent phi as r times d theta by dr. Let's close it in a nice bracket, in a nice box. Okay, this is it. That's it. So you can see that phi was the angle between the radial segment and the tangent line. Okay, so tangent line is actually it's a line that was passing through this point of contact, this point of tangency r theta. Now if I just try to draw, I'm just trying to manage an orthogonal trajectory of this curve. Okay, so once this is simply a single curve, we can apply the same concept on the family of curves as well. So here, as we are discussing the curve in terms of polar coordinates, so I'm going to represent this curve as r theta and some value of constant. Okay, once when I keep on changing the value of constant, I'm going to have multiple curves belonging to the same family r theta, okay, containing this point on it. Okay, so orthogonal trajectory of this family of curve, or for this curve, is what? It is going to be that curve whose tangent line at this point of contact will be exactly perpendicular to this tangent line. Okay, so how we are going to understand this? For this purpose, I just prefer to draw here a figure that will help us to understand the concept more deeply. So let me just draw that figure. So this was our point r theta. Okay, and this is the tangent line making an angle C, and this is the radial segment that I have just drawn over here making angle theta with the x-axis, and between and the angle between the tangent line and the reference radial segment, because we are discussing the polar coordinates, the angle was phi. This was the angle phi, and the slope of this line with respect to the radial segment was so determined through this formula. Okay, now what I'm going to do right now, I'm going to draw a tangent line, or another line which is right perpendicular to this one, first of all, because I don't know what could be the orthogonal curve for this given curve. So in order to determine the direction or the layout or the design or the shape of the curve, which is orthogonal trajectory for this curve, I'm just going to make a corrupt technique just for understanding. For that purpose, what I'm going to do, I'm going to draw a line which is right perpendicular to this tangent line T. Okay, so it would look something like this. So let me just draw it. Okay, that's how it looks like. All right, so what should be the orthogonal trajectory for this family of curve? Maybe it looks something like this. It's quite a rough thing, but I hope you can get that. This is it. Okay, because the line which is Oh, I'm sorry. It must be something like this. I'm sorry for that. Let me just remove this thing. Well, it could be something like this, maybe. Or it could be like this as well. So this line, tangent line, is passing through this point with respect to this curve. And this tangent line is exactly perpendicular to this tangent line t. Okay, so these red curves are behaving as the orthogonal trajectory for this curve. Okay, so no matter, you just keep on changing the value of c. Just keep on changing the value of c, and you are going to have a multiple curves that is called the family of this curve belonging to this function with respect to changing value of c. And these curves are said to be the orthogonal trajectory for this family of black curves. It's like that. So what you have understood from here, it is that the slope of this line of this tangent line is perpendicular to the slope of this tangent line. Let us try to see one more thing. You can notice that this is your angle phi. This is the reference segment or the reference axis in polar coordinates. So this d dash is making an angle 90 plus phi along with the r segment or r axis or the radial axis. It is making 90 plus phi over here, you can see. Okay, so if we just represent this angle, the angle between this tangent line and the radial segment, we just call it phi 1, and it is equals to 90 plus phi. Okay, so if phi 1 is the angle between the orthogonal trajectory tangent line along with the radial segment, then phi 1 can be interpreted as this. Okay, so if we just apply tangent at both sides, like this, we just gently put the formula, and we know the tangent 90 is infinity, so we have to apply the reciprocal process here just to avoid the undefined condition. Okay, so tangent phi 1 is equal to, I can make a nice adjustment like this. So you can see that this is 1 upon infinity, so it will be 0. And this is also 1 upon infinity, so it is also 0. So you're having this stuff over here. So this thing tells me that the slope of this tangent line and the slope of black tangent line and the slope of the red tangent line is equals to -1. So it means they are perpendicular to each other. Okay, so what next do we have to do? We just assume here that let the differential equation of our black family of curve is represented by, for example, like this. So this thing reveals that PDR is equals to -q d theta. So where P and Q are the function with respect to R and theta, like that. So d theta upon dr is equal to -P upon Q. So this is the, if you just multiply both sides by R, and we are having stuff like this. So this is what this is representing, the slope of the tangent lines. This is the general form of the slope of the tangent line with respect to the radial axis or radial segment axis. Okay, so if we just talk about, if this is something that you call tan phi, if tan phi is equals to this, then tan phi 1, or the tangent of the orthogonal trajectory, will be the negative reciprocal, will be the negative reciprocal of this slope. Okay, so it'll be equals to q upon pr. Okay, and this thing can be interpreted in this way. Sorry, q upon pr. Now you can swap the values here and there. You can apply method of separating variables method, whatever the method of solving the first order ordinary differential equations. You can use those methods, find out the solution of this differential equation. Once when you find out the solution of this differential equation, that function, definitely the solution of differential equation is the function that's going to satisfy it. So that function, r theta having some constant, is said to be representing the orthogonal trajectory of the family of curves of this function. Okay, so this is exactly a theory that I just endeavored to explain you before approaching to the examples. Okay, so that's all for today, and if you find this video helpful, just subscribe my channel, spread this video as much as you can, and hit on the like, and don't forget to put your comments in the box below. Take good care of yourself. Inshallah, in the next video we'll try to see the examples of the related topic. Allah Hafiz.